So, in this module we will see how we can control the speed of these induction machine drives, not just motors, but also in the as a generator here. But although we will talk mostly in terms of motors, but certainly it should apply to generators. So, here is the block diagram that we have, and we can see that we have a power coming from the line, and then we have a power processing unit, and then this dotted lines that you see in the sensors, they may or may not be there, but even without them we should be able to adjust the speed of these drives here in an energy efficient manner. Okay. So, if you look at the rotor losses, first of all, the power crossing the air gap is the torque times the synchronous speed, and then power delivered to the rotor is at the shaft, not the rotor, but to the shaft, from the rotor to the load or to the shaft, is the electromagnetic torque times the rotational speed, omega m. So, the difference of these two gets lost in the rotor resistance, and that's electromagnetic torque times omega slip, and therefore, our aim should be to operate these machines at as small a slip speed as possible. And so, we can see how this can be done, and so here are some plots here. We have to supply certain torque T sub L and at certain speed omega sub m, but depending upon the maximum flux density in the air gap, you can see that we have different characteristics. So, as this flux density is increasing, we can see that the slip at which this machine would operate becomes smaller and smaller. So, under the omega sync 3 and with higher flux density, we see that we have the smallest slip. So, the moral of this slide, if you will, is that we should operate at the rated flux density in the machine. Of course, we cannot go beyond the rated, otherwise the machine would saturate, but certainly we should be operating at the maximum flux density. So, let us look at the torque speed characteristics here with this flux density assumed to be at its rated, and you can see that for different frequencies then we have different torque speed characteristics where F1 is smaller than F rated and F2 is smaller than F1 and so on. And we can see that these frequencies then give us different synchronous speeds along the vertical axis. They are listed, and if, for example, the load torque that we are supplying is constant, and that's shown by a vertical line in the figure on the right, then you can see that by adjusting the frequency of applied voltages, we can adjust the speed. So, at F rated, this machine would operate at omega m rated. At F1, it will operate at speed omega m1, and in this case where the load torque is constant, keeping this flux density at its peak, the slip speed under all these operating conditions is the same. That is, omega slip 1 is the same as omega slip rated and the same as omega slip 2. Now, let us see what we have to do to maintain this flux density at its maximum value. So, let us look at the circuit on the left here, which is the complete equivalent circuit that we had derived in an earlier module, and we can see that at if we keep the slip speed small, then this in the rotor branch, the resistive part dominates the inductive part, and therefore, it is reasonable to assume that we can neglect that as shown on the right. And so, it's what we have then is if you draw the phasor diagram of the circuit and take this EMA as the reference phasor, we will see that the rotor branch current is in phase with that IRA prime, as shown here, and the magnetizing current drawn is 90 degrees lagging behind, and then we can add the drops across the stator resistance and stator leakage inductance due to these two components of the current IA, and IA is of course made up of IRA prime and IMA. So, all those are shown, phasors are shown over here. So, what and the resultant is the applied voltage VA phasor. So, the moral of the story here is that as far as the magnitude is concerned, we do not need to worry about the perpendicular part, because that does not really change the amplitude very much. So, we just need to take into account the horizontal part, and so what what that says is that we can actually, if you look through the material in the book, that in order to keep the flux density at its rated value as an approximation, we can do so by keeping volts per hertz. The applied voltage divided by the frequency at which it is applied is constant. So, that is a fairly at least it is a first order approximation. But if you want to be more careful, then what we can conclude here is that V over F would give us a straight line going to the origin, shown by the dotted line over here, but in addition we need to add the drop across the stator resistance, and that depends upon the load on the machine, and therefore IRA prime as shown here. So, to be to be more careful and to actually get this flux density to come out to be at its rated value, the characteristic is shown by the solid line here, and you see that at the rated torque we need to apply certain voltage boost in comparison to, or in addition to, what V over F type control would suggest. So, here is a summary where we have seen the block diagram of speed control. We have looked at rotor losses and how we can minimize the slip speed by keeping the flux density at its rated value, and what do we have to do to get that condition, and which is approximately speaking V over F control, but we can include the drop across the stator resistance.